Hello, today I'm going to continue with the audio lessons on ordinary level organic chemistry. Chapter 2, terms used in organic chemistry. But in our last class, we actually saw chapter 1, introduction to organic chemistry. There, we looked at two definitions for organic chemistry. The first of this definition was organic chemistry is a study of substances of plants and animal origin. That is, substances that emanate from living things. And we equally saw another definition, that organic chemistry is a study of compounds containing carbon, with the exception of simple compounds like the carbonates, carbon monoxide, carbon dioxide, and metallic carbides. Now, the second definition was so important in the sense that it grouped compounds like the carbonates, oxides of carbon, and metallic carbides under inorganic chemistry. These compounds are studied under inorganic chemistry, and we equally saw what we call the constitutive elements of organic compounds. We have the main element, which is carbon. We have the usual element, hydrogen and oxygen, and we have what we call occasional, that is to say from time to time we find these elements, and among them we could name nitrogen, the halogen, phosphorus, sulfur, and some metals. These were the constitutive elements of organic compounds, and we went further to explain why carbon has the capability to form a large number, a variety of compounds, and among these we mentioned three reasons. And the first one was that carbon have the capability to catenate, that's self-linkage ability. And the second one was that carbon has the capability to combine with hydrogen, oxygen, nitrogen, and the halogen with ease. The word ease is very important here because we have other elements capable of combining with others in the periodic table and forming compounds, but they do this with difficulties. Now, we equally said that carbon has the ability to form single, double, or triple covalent bonds, and went further to look at what we call the characteristic features of organic compound. We could cite covalent nature, polarity, solubility, and so on and so forth. So that is a summary of what we did in chapter 1, introduction to organic chemistry. So you listen attentively, follow up attentively as we discuss chapter 2 today, terms used in organic chemistry. For you to understand a subject very well, namely the subject of organic chemistry, you need to understand the language of that subject. I mean the jargons of the subject. So we want to discuss about the jargons of organic chemistry. Some of these terms probably you're already familiar with, but as a form of revision and new knowledge, we have to learn them to know the terms that we'll be using as far as organic chemistry is concerned. So I will advise you once more, if you have not subscribed to my channel, OBI.S.N, Dr. Science, you do well to subscribe so that you enjoy all the 14 chapters of ordinary level organic chemistry that I'll be teaching via this channel. I'll be back in a minute with audio lectures on chapter 2, terms used in organic chemistry. Welcome back. Chapter 2, terms used in organic chemistry. The first term is electronic configuration of the carbon atom. By definition, the electronic configuration is the arrangement of electrons in the different shells of an atom. Now, the electronic configuration of carbon is 2, 4. That is, it has 4 unpaired valence electrons in its outermost shell. This enables the carbon atom to form single covalent bonds by sharing electrons with neighboring atoms, which may be carbon atoms or atoms of other elements. so that the outermost shell of its atom is completely filled. Alkanes have a tetrahedral shape with a bond angle of 109 degrees. Alkenes have planar shape with a bond angle of 120 degrees. And alkynes have a linear shape with a bond angle of 180 degrees. The shapes of alkenes and alkynes are shown in the following figure. The second term is homologous series. A homologous series is defined as a family of organic compounds which follows a regular structural pattern in which each successive member differs in its molecular formula by -CH2- group. Now, each individual member is called a homolog. Examples of homologous series and their general molecular formulas are alkenes, CnH2n plus 2. Alkenes, CnH2n. Alkynes, CnH2n minus 2. Alkanols, CnH2n plus 1 OH. Carboxylic acids, CnH2n plus 1 COOH, etc. as shown in the following table. It should be noted that lowercase n for carboxylic acid is greater than or equal to 0, since the first member of carboxylic acid homologous series is methanoic acid, and we already have a carbon atom in the carboxylic acid functional group. Now, let's take a closer look at some characteristics of a homologous series. The first one is that all members share a general molecular formula, e.g., CnH2n plus 2 for alkenes. 2. Each successive member differs in its molecular formula by the addition of a CH2- group and in its relative molecular mass by an increase of 14. Since a carbon atom has a relative atomic mass of 12 and hydrogen has relative atomic mass of 1, and since we have 2 hydrogen, we have 2 plus 12, that gives 14. So each successive member differs from its molecular formula by a mass of 14. The third characteristic is that the physical properties of the members change gradually as the number of carbon atoms per molecule increases. In the case of alkanes, for example, we have C1 to C14 are gases at room temperature and standard pressure. C5 to C17 are volatile liquids, and higher members are wax-like solids. Now, the melting point and densities of the alkanes also increase, while their solubility in water decreases down the series. The properties of the first 10 members of alkane series are summarized in the following table. The fourth characteristic of a homologous series is that all members show similar chemical properties. For example, the alkanes are unreactive under ordinary conditions. They burn in air, forming carbon dioxide and water. They undergo substitution reactions with other substances such as halogens. The fifth characteristic is that all members can usually be prepared by using the same general methods. For example, alkanes can be prepared by the action of hot soda lime on the appropriate sodium salt. The third term used in organic chemistry is alkyl group. The general term alkyl group includes all groups derived from alkanes by the loss of a hydrogen atom. The general formula of an alkyl group is CnH2n plus 1. Alkyl groups are named after the parent alkanes by replacing the ending or suffix "in" by "il", e.g. methyl CH3-, ethyl C2H5-, etc. Alkyl groups are given the general symbol of capital R. Sometimes R may stand for more complex groups than just simple alkyl groups, and sometimes it may represent a simple hydrogen atom. Alkyl groups influence the physical properties of a compound, e.g. solubility. The polar hydroxyl group in the alkanols promotes solubility in water, but the nonpolar alkyl group opposes it. For alkyl groups larger than C4H9-, this opposing effect is sufficient greatly limit the solubility of the compound in water. The fourth term used in organic chemistry is functional group. By definition, a functional group is an atom, a radical, or what we call group of atoms, or a bond common to a homologous series, and which determines the main chemical properties of the series. Now, each functional group has its characteristic properties. When two or more functional groups occur in a molecule, the properties of one are often modified or influenced by the presence of the others. Thus, the presence of the functional group or groups determines the chemical properties of a homologous series. Now, let's look at the table below, which gives the homologous series derived from alkanes, their general formulas, and their functional group. Capital R and capital R prime may be the same or different alkyl groups, or they may represent a more complex group than an alkyl group. Now, the fifth term used in organic chemistry is saturated organic compounds. Saturated organic compounds are compounds containing atoms joined only by single covalent bonds. For example, alkanes are saturated hydrocarbons, e.g. ethane and propane. Also, the sixth term used in organic chemistry is unsaturated organic compounds. By definition, unsaturated organic compounds are compounds containing carbon atoms joined by double or triple covalent bonds. For example, alkenes and alkynes are unsaturated hydrocarbons, e.g. ethene and ethine. Now, the seventh term used in organic chemistry is formulae of organic compounds. Under formulae of organic compounds, we are going to look at empirical formula, molecular formula, structural formula. Now, let's start with the empirical formula. By definition, empirical formula is the simplest formula of a compound. It shows the relative numbers of each kind of atoms in a molecule of a substance. It is found by determining the percentage composition of the substance by quantitative analysis. Also, the molecular formula shows the actual or exact numbers of each kind of atoms in a molecule of a substance. It is deduced from the relative molecular mass of the substance. and its empirical formula. Now let's look at the third term under formulae of organic compounds, that is structural formula. The structural formula shows how the atoms are arranged within the molecule of a substance. It is therefore more informative than the molecular formula, which could be representing more than one substance. The structural formula equally shows which atoms are linked together and how they are linked by using conventional symbols. That is, dash for single covalent bond, an equal sign for double covalent bond, and an equivalent sign for triple covalent bond. The structural formula can also be written in the condensed form, that is to say, condensed structural formula, where the alkyl and functional group present in the molecule are shown arranged in the correct order. Condensed structural formula is usually preferred because it indicates the functional groups present in the substance. The structural formula is usually determined through various spectroscopic methods. The structural formula of ethanoic acid, as well as its condensed structural formula, are as follows. It should be noted that because of legibility and convenience, we prefer to use a condensed structural formula in a sentence. Dear students, this is the end of chapter 2. In our next class, we are going to start with chapter 3, the IUPAC nomenclature for aliphatic compounds. If you don't want to miss this lesson, as I told you in the first video, for ordinary level organic chemistry, simply subscribe so that if I put up any video, if I upload any video, you are going to receive the notification. You watch it. Your children as well can watch it. And remember to like, comment, and share this video. Don't forget to subscribe. It's very important because these lessons are going to take you through your ordinary level organic chemistry. A word to a wise is enough. Goodbye for today.